right, so this is this figure from your book that shows the overall structure of a spectral line. Basically, we've got some things that contribute with the damping profile. There's the collisional broadening and the pressure broadening and the natural broadening. And the dark outline shows the damping profile. The Doppler profile, Doppler broadening plus turbulent broadening, dash line shows the Doppler profile. And these have been scaled to have the same equivalent width. So there's the same area under the curve in both cases.
Oh,
Yeah, so that's just so that you can kind of compare them apples to apples with one another. But you have to keep in mind that normally what happens is that the damping profile would be narrower, would have a much narrower equivalent width than the Doppler profile does. But what this is showing is what I alluded to before, is the idea that the damping profile decays less rapidly in the wings, if you will, than the Doppler profile does. And so what tends to happen is when you look at the overall spectral line, the core near the central wavelength is dominated by the Doppler contributions, and the wings are dominated by the damping contributions. And so we say that typically a spectral line has a Doppler core and damping wings, is the terminology given to that. So let's write that out to make it all official-like. Total line profile including all these effects. Is called the Voigt profile. It's a Voigt profile. I'm going to infer from that that it was first deduced by a person whose last name is Voigt. Yeah. And in general, the Doppler profile dominates near lambda naught due to its greater width. It's greater full width at half max. But because it falls off exponentially, as opposed to the damping profile, the damping profile dominates far from the core. So what we say is that the line exhibits, as I said before, a Doppler core and damping wings. damping rules. And then finally, we'll talk about subdwarfs. Subdwarfs. Okay. Subdwarfs. Yes. So remember, if we have a kind of generic sketch of, HR diagram, so T of course increases to the left, and L increases up. Got the main sequence, luminosity class 5, and the subdwarfs, luminosity class 6, which are also main sequence stars, but they are low metallicity main sequence stars. Low metallicity main sequence stars. So they're a little shifted from the main sequence for higher metallicity stars like the Sun. There's no sharp border between them though, it's a continuum. Most free electrons in a cool star's atmosphere come from metals because they don't hold their outer electrons very tightly. They're easily ionized, right? In a hot star, hydrogen becomes ionized, because remember about 10,000 Kelvin is where hydrogen becomes ionized. So in a hot star's atmosphere, you get plenty of electrons from just the hydrogen. But in a cooler stellar atmosphere, most of the free electrons come from metals. Most of the free electrons come from the easily ionized metals in the astronomer's sense. In a cool star's atmosphere, since H stays neutral for T well below 10,000 Kelvin, like the Sun, for example, or the temperatures more like 5770, or often we'll just say 5800 Kelvin. in subdwarfs, you got a lower metallicity, which means lower electron number density.
Because there is lesser number of free.
Yep. And remember that the primary source of continuum opacity in a star like the Sun is the H- ion, where a hydrogen acquires an extra electron that is very loosely bound so that any visible wavelength is able to ionize it. Everything in the visible spectrum has enough energy to strip off that electron, so that's the primary source of opacity in a cool star's atmosphere. So there is a lower continuum opacity. These stars' atmospheres are less opaque than the atmosphere of the Sun because of their much lower H- abundances. So we can see deeper into these stars. So the photosphere, the layer where most of the light is last scattering before it goes into space, this photosphere is at a hotter, deeper level of the atmosphere. So we've got a smaller effective radius that we would see. And higher surface temperature for a given luminosity. Higher Tef for a given luminosity, because remember that Tef is the temperature of the layer at an optical depth of 2/3, which is deeper for these stars.
I see. So, is it still, is TEF still at an optical depth of 2/3 even for these stars?
Yeah.
Okay.
Essentially, again, that's using the Eddington approximation, blah, 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 but it's a decent approximation. So, rule of thumb is that it's a good approximation to say that Tef is the temperature of the layer at an optical depth of 2/3, which is deeper and hotter in these stars than it is in a star like the Sun. So if you had a star of the same luminosity as the Sun, but with less metallicity, you'd see deeper down into its atmosphere, and so it would look both smaller and hotter than the Sun does.
I see. Okay, so it's like a matter of, it's like,
Right, so the luminosity is 4 pi r squared sigma Tef to the 4th. R gets smaller and Tef gets bigger in a compensating way. So the star would appear smaller, a little smaller, and a little hotter than the Sun. So in other words, like, if that's the Sun, a luminosity class 6 star of the same luminosity would be over here at a higher surface temperature.
okay, now I understand.
That's the idea.
Yep. Okay, so most of these subdwarfs are the higher temperatures and
They appear, they would have a higher effective temperature. The luminosity is the same, but because they're more transparent, if you looked at them, they would literally, because the Sun surface is its photosphere. That's the layer, what we see as the Sun surface is the layer where light last scatters on its way out to us. And so for one of these stars, If you put it side by side with the sun, because its atmosphere is less opaque, you can see further down, it would look slightly smaller than the sun, slightly hotter than the sun, such that it still would have the same luminosity. So a subdwarf with the same luminosity as the sun will look hotter and smaller than the sun does, and that means that the point that represents it shifted over to the left a little bit on the HR diagram. As I say, mass correlates with luminosity, but the luminosity changes a bit while the star's on the main sequence. So I'll just leave it at luminosity there. So that's what's happening with the subdwarfs. It's better to say that they've been shifted to the left rather than shifted down.
I see, because you're talking about in terms of temperature.
Yeah, it's really more that for a given luminosity, it's better to say that for a given luminosity, the temperature is higher. It's also true that for a given temperature, the luminosity is lower, but if you look at the physics of what's going on, it's better to think in terms of, if you took the sun and lowered its metallicity, it would still be producing, like you just swept out most of the metal ions and replaced them with an equal mass of hydrogen. Then the sun's core would still be producing the same luminosity because it still would have the same amount of weight above it that it has to support. So the luminosity wouldn't change, but the more transparent atmosphere would let you see deeper into it, and so that would make the sun appear to get smaller and hotter, even though nothing has really changed on the inside.
I see.
But you know, a star is not a planet where it's got a well-defined surface, it's a ball of gas. So what you see as the surface is something of an illusion. It's just the layer from which most of the light is coming. Most of the light last scatters in what you see as the surface of the star, even though it has nothing that really defines the surface per se, because it's just a big ball of gas.
There's nothing solid.
There's nothing solid there, right? The sun looks like it's got a solid surface, but it's an illusion because the photosphere is only about 400 kilometers thick. And even saying that is overdoing it, because it's not like you can't see anything below 400 kilometers. It's just that by the time you're 400 kilometers thick, you're hardly getting anything from below that level. But you're still getting some stuff. So there's no such thing really as the surface of a star because it's a ball of gas. But the sun looks like it has a nice sharply defined surface because most of the light's coming from a layer around-ish 400 kilometers thick, which is very tiny compared to the sun's size, such that if I drew a picture of the sun like this, that line is thicker than the photosphere is on the actual sun. That line is thicker compared to the radius of my circle than the sun's photosphere is compared to its radius. So the sun looks like it's got a very sharply defined surface simply because the layer from which we're getting most of the light is very thin compared to the sun's size. When you have if you have a giant star where the atmosphere is distended, the photosphere is much, much thicker. You can see a lot further into it. So that if you looked at a red giant, or even more so a red supergiant, people don't typically show it that way when they make paintings. They make it kind of look like it's got a nice, sharp-looking edge like the sun. But in fact, if you were looking at like Betelgeuse from anywhere where you could see it, it would have a fuzzy edge, because you can see quite a distance into it because of the fact that its outer atmosphere is extremely thin. So Betelgeuse wouldn't appear to have a nice sharp edge like the sun. It would look fuzzy on the edges. And you could actually see through its outer layers. If a star went behind it, you'd be able to see it while it was partly behind what you were seeing as the outer parts of Betelgeuse.
That's pretty cool.
So it's more accurate to say they've been shifted to the left of the main sequence than one magnitude below the main sequence. for chapter, whatever we were just doing, chapter 9. So now we're ready to move into chapter 10, which is the equations of stellar structure, writing down the differential equations that describe a stable star.
Wow.
Yes.
Wait, wasn't it the sun?
What's that?
I thought it was the sun in next chapter.
No, I think that's chapter 11, if I'm not mistaken. I think so. I think that's the one after that.
Yeah, probably.
I think so, yep. Because I think if I recall, the book develops the equations of stellar structure and then applies them to the sun. Yes.
Let's go. Stellar structure.
Yes, so this is some stellar stuff we're studying here. Okay, I should take this off. My poor black coat has white chalk dust all over it. But then my black shirt has white chalk dust all over it. As far as I can tell, though, chalk dust is not harmful to human lungs because otherwise professors and teachers would have much shorter lives. And I'm not aware of any epidemiological studies that indicate that. So apparently lungs can handle chalk dust. Yeah, he said before choking. Famous last words. Lungs can.
And as you cough, a big cloud of
Big
chalk.
cloud of chalk dust comes out. That's right. Yes. So we are in chapter 10 now. The equations of stellar structure. So there's 4 of them. And several of them are really pretty easy to derive. Like you could just, it would be not unreasonable to say you should be able to just start and derive it from scratch. And then one of them is like not easy to derive. So we'll start with hydrostatic equilibrium. So I should say that we're looking at static stellar structure. We're assuming the star isn't changing with time. It's so if you really want to do it upright, you have to put in the time dependence. You have to put in the fact that as the star is burning its nuclear fuel, the amount of hydrogen in it is decreasing with time and so on and so forth. We're going to be looking at a star which, like the sun, is in the middle of its main sequence life, and so the time scales over which the sun's structure changes appreciably are at least hundreds of millions of years. So to a good approximation, we can consider the star to be static, not changing with time.
I see.
So, hydrostatic equilibrium. This describes the balance between pressure and gravity. A star is in a constant struggle, if you will, wherein it's not literally a struggle, but gravity is trying to make the star crush itself, and that's balanced by pressure, which keeps that from happening. Gravity in a sense is trying to make the star puff out. Pressure is trying to make the star puff out. Gravity is trying to pull it together. And in equilibrium, in any given layer, there's a net upwards pressure force that's equal to the weight of that layer. And that's what hydrostatic equilibrium describes.
It matches the F gravity.
Yep, the upwards pressure force matches the downwards gravity force is what the equation of hydrostatic equilibrium says. So this describes the balance between the net upward force of pressure and the downward force of gravity every layer. Where a star doesn't literally have layers, but we can mentally break it up into thin layers. So what we're going to do is imagine that we were taking a little chunk inside the star, and the center of the star is way down there, so this is the radial direction. And this little piece of the gas in the star has thickness dr, a little change in radius away from the center. So the bottom of it is at radius r away from the center. The top of it is at radius r plus dr. A is the cross-sectional area of our little can, if you will, imaginary can of star stuff.
Star soup.
Yeah, star soup, that's right. Campbell's Chicken and Stars. That's an actual thing you can get from Campbell's.
Produced naturally within the star.
That's right, yes. In a sense, yes, because all those elements needed to make it, except for the hydrogen, came from stellar nuclear fusion. So P of r plus dr is the pressure at r plus dr, and that's going to produce a downwards force on our plasma blob, our plasma can, if you will. And the pressure at radius r pushes up on the bottom. So the net pressure force is going to be, we'll call it F sub P, the net pressure force. That'll be minus A times P at r plus dr, because that's pushing towards negative r. That's pushing not negative, pushing downwards, pushing towards decreasing r. So in other words, we'll take positive to be an upwards and downwards to be a negative force. Okay? So the pressure force from the top is minus the area times P of r plus dr, because pressure times area equals force. Pressure is force per unit area. So the bottom is plus A P of r. And then that's going to be approximately P of r plus dr is approximately P of r plus dP of r, dP dr times dr. So in other words, dP dr would be the limit as dr approaches 0 of P of r plus dr minus P of r over dr, right? Change in the pressure over the change in the radius. So this says that dP dr times dr, to a good approximation, is P of r plus dr minus P of r. In other words, the change in P is approximately the derivative times the change in r, P dr times dr. Okay. Another way to look at it is as being the first two terms in a Taylor series. P of r plus dr is P of r plus dP dr times dr plus 1 over 2 factorial second derivative of P with respect to r, dr squared, and so on and so forth. You can also view it as the first two terms in a Taylor series, but you can also look at it like this. It's just the approximation that...
This is the derivative definition, right?
Yeah, it's the definition of the derivative, right?
Yeah.
So we're just using the fact that dP dr is approximately delta P over delta r. And we're calling delta r dr anyway, so.
Nice.
So in other words, P of R plus dr is approximately P of R plus dp dr times dr. And then we're subtracting off P of R over here. And so, in other words, the net pressure force is minus A dr times dp dr.
I see.
So notice that it's a pressure gradient that gives rise to a force. If dp dr were 0, there would be no net pressure force because the pressure would be the same on the top and the bottom,
Which would
and they cancel one another. So for pressure to produce a force, it has to vary with position. So it's really, pressure itself doesn't produce a force, it's pressure gradients that produce net forces in a gas. And then we'll notice A times dr here is the volume of the cylinder. Since A dr is the volume of the cylinder, note that minus dp dr is the net pressure force over that little volume of the cylinder is, I'll call it the dV because it's a little thing, is the pressure force per unit volume in the fluid. Remember, fluid refers to both liquids and gases, anything that can flow as a fluid. So minus the pressure gradient is the pressure force per unit volume in a fluid. And this is very, very general. Oops. We're doing this in one dimension. If we were in 3 dimensions, instead of minus dp dr, it would be minus the gradient vector of P, minus grad P. If you look at the mass of the fluid in the cylinder, that'll be its local density at that place times the volume. So that'll be dm, a little chunk of mass, is rho A dr. Where rho is the mass density, which in general is a function of r, it depends on r, u star. So dm is rho A dr. So the weight of the cylinder, the force of gravity on it,
is
is gonna be minus rho g. Right. Minus rho g ADR, where g is the local acceleration due to gravity.
negative GMV.
G will be minus capital G, the gravitation constant, m sub r over r squared. M sub r equals mass inside radius r. So I'm invoking the fact that gravity, because it's an inverse square law of force, just like the electromagnetic force, it obeys Gauss's law. Remember that in electromagnetic theory, we learned that only the charge, if you have a spherically symmetric charge distribution, only the charge within that radius contributes any net electric force. Gravity works the same way.
Yeah.
Only the mass within radius r contributes any force. So
mass enclosed.
the mass enclosed, exactly. So if this is radius r, m sub r is the mass inside radius r, and minus g m sub r over r squared would be the local acceleration due to gravity, because the force on a little chunk